Today we are going to start chapter number 2, Vectors and Equilibrium. Many of you may have played this game. You can see the launching of birds at different angles with different magnitude or at different directions. It is the beauty of vectors. We can use different directions and different magnitudes, and we can launch it at different angles by the help of vectors. As we know that vectors have magnitude as well as direction. So they are used in many applications which we use in different places. In this game you can see that people are applying force on this person, and in return this person is also applying force on these people. So force is on right side and on left side too, because it has magnitude with which we can define how much force is applied, and as well as direction, because force is applied by these people is in some direction and force applied by this person is in another direction. So it is another example of vectors. As we have started today chapter number 2, Vectors and Equilibrium, we will discuss vectors, Cartesian coordinate system, and addition of vectors. Let's start with vectors. A vector quantity is a quantity that has magnitude as well as direction. For defining scalar quantities, we do not need direction, we only need magnitude and unit. But for defining vectors, we need magnitude as well as direction. For example, when we calculate the length or mass of anything, we do not need direction to define length or mass. But when we talk about velocity, acceleration, force, etc., we need direction to define these quantities. So all those quantities that are defined by magnitude, unit as well as direction are called as vector quantities. Few examples of vector quantities are given here, such as velocity, force, displacement, and acceleration. These are only few examples of vectors. Representation of a vector. Vector can be represented by two ways: symbolic representation and graphical representation. Symbolic representation of a vector. Vector is represented by bold-faced letters such as A, D, and R. Alphabets are written in bold-faced letter. Vector can also be represented by a small arrow above the physical quantity. So vector quantity A should be written as small arrow above the A letter. Symbolic representation of different physical quantities are shown here. Velocity is a vector quantity and symbolically it is represented by small arrow above the letter V. Force is a vector quantity and symbolically it can be represented by small arrow above letter F. Displacement is a vector quantity and symbolically it can be represented by small arrow above the letter S. And acceleration is also a vector quantity, so symbolically it can be represented by small arrow above letter A. These are a few examples of symbolic representation of a vector. Magnitude of a vector and its symbolic representation. Magnitude of a vector tells us the quantity of that vector, means how much that vector is. Magnitude of a vector tells us that how much that vector quantity is. For example, if force is given as 50 Newton, So 50 is magnitude of vector and Newton is unit of vector. And F is force, that is vector quantity, equals to 50 Newton. So 50 tells us that how much force is applied, and that is the magnitude of force vector. The magnitude of vector is written as vector with mode, or in between two parallel lines we can write a vector and it represents a magnitude of vector. It can be simply written as A or mode of vector A. Magnitude of velocity can be written as V or mode of V with small arrow above V. Similarly, we can write magnitude of different vector quantities, and few examples are shown here. Graphical representation of a vector. Vector is represented by straight line with arrowhead at its one end. Arrowhead represents direction of vector. The starting point is called origin and end point of vector is called head point. This length of straight line shows the magnitude of vector quantity. With increasing this length of straight line, magnitude of vector quantity increases. Here you can see that Fahad is kicking the football. For small force applied by Fahad on this football, we can graphically represent force with small straight line with arrowhead at its one end. For big force, we increase the length of this straight line with arrowhead because the magnitude of force is increased. So for greater magnitude of force, we increase the length of this line. The set of two or three mutually perpendicular lines intersecting at a point is called Cartesian coordinate system. The lines are called coordinate axes. Here we have two lines. These lines are intersecting each other. Green line is showing horizontal axis, that is called as x-axis, and red line is showing vertical axis, that is known as y-axis. X-axis and y-axis are intersecting at a right angle 90 degree at a point here. The x-axis and y-axis are normally on the plane of the page or screen. The z-axis comes directly out of the page or screen at the origin, which is not shown here for simplicity. Representing a vector in plane. For representing a vector in plane, we consider a Cartesian coordinate system that is simply two axes, x-axis and y-axis, intersecting at point O. Suppose that we have force vector F, that is 50 Newton, making an angle of 30 degree with horizontal axis. For drawing this force of 50 Newton, we consider a scale 1 centimeter is equals to 10 Newton. So 50 Newton is equals to 5 centimeter. And for representing this 50 Newton force, we can take a scale of 5 centimeter. The angle is measured from the positive x-axis in anti-clockwise direction. It's for convention. So by this method, we can write vector f in xy plane. Steps followed in representing a vector in plane are: first of all, we draw a Cartesian coordinate system, and then we select a suitable scale, and then we draw a line in the specified direction. Cut the line equal to the magnitude of vector according to the selected scale. In our case, we have 50 Newton force, that is equals to 5 centimeter. So we take this line equals to 5 centimeter. put an arrow in the direction of vector. Representing a vector in a space. It is represented by three angles which the vector makes with x, y, and z axes. For representing a vector in space, we take three axes: x-axis, y-axis, and z-axis. The direction of vector in a space is specified by three angle symbols: alpha for x-axis, beta for y-axis, and gamma for z-axis. Unit vector. The dimensionless vector having magnitude 1 and used to represent the direction of a vector is called unit vector. It is represented by a head above the vector quantity. Its formula is unit vector is equals to vector divided by magnitude of the vector. So this vector is divided by its magnitude that gives its unit vector. In this Cartesian coordinate system, unit vectors are represented by I cap, j cap, and k cap along x, y, and z axis respectively. These unit vectors are showing the direction along the axis. I cap is a unit vector directed along the positive x-axis. J cap is a unit vector directed along the positive y-axis. K cap is a unit vector directed along the positive z-axis. Unit vectors do not change the magnitude or dimensions of physical quantities that are vector quantities, but unit vectors only tells the direction of these vector quantities. One thing you should know that vectors cannot be added, subtracted, and multiplied by ordinary algebra because vectors have both magnitude and direction and they obey the rules of vector algebra. Addition of vectors. Addition of vector is possible by two methods: graphical method and analytical method. Graphical or geometrical method for addition of vectors. We can use head to tail rule for adding vectors. According to this rule, select a suitable scale, sketch all the vectors according to the scale. As in previous slide, we represented force 50 Newton on centimeter scale. So you have idea that how to select a suitable scale, and then we sketch all the vectors according to the scale. As here vector A and vector B are sketched according to the scale. Now join the tail of the second vector B to the head of first vector A. By joining the tail of the first vector, vector A, to the head of the second vector, vector B, and putting an arrow on the line pointing away from the origin gives the resultant vector. To determine the magnitude of R, measure the length of R and convert it according to the selected scale. To determine the direction of R, measure the angle of R with x-axis. Vector addition is commutative. Let's prove it. Consider vector A and vector B. Let these two vectors represent two adjacent sides of a parallelogram. We construct a parallelogram. Vector addition is commutative, just like addition of real numbers. Here in this figure, resultant vector of vector A plus vector B is same as resultant vector of vector B plus A. So we get A plus B is equals to B plus A. It is commutative property. It means that the order in which the vectors are added has no physical significance. When two or more vectors are added together, they must all have the same units and they all must be the same type of quantity. Addition of more than two vectors. Now we have three vectors A, B, and C. We can add vector A, vector B, and vector C together by selecting a suitable scale and then using head to tail rule. So the tail of each vector is on head of the previous vector according to the head to tail rule. Here tail of vector B is on the head of vector A and tail of vector C is on the head of vector B. Vector D, that is resultant vector, and its tail is connected with the tail of vector A and its head is connected with the head of last vector, that is vector C. For determining the D resultant vector, we can calculate the length of D and convert it back according to the given scale. It will give the magnitude or size of the resultant vector D. Addition of more than two vectors, as we discussed in previous slide, that commutative property hold good for addition of more than two vectors as well. Here we have five vectors: vector A, vector B, vector C, vector D, and vector E. When they are added in different order, still the sum is independent of the order of the addition. Hence the commutative property hold good in this case as well. Subtraction of vectors. There is no direct method for determining the result of subtraction of two vectors. Even for subtraction, we use the method of addition, as if vector B supposed to be subtracted from vector A, then first we find negative of vector B, which is minus vector B, and then we add this negative of vector B with A vector as shown in this figure. We have two vectors, vector A and vector B, that are graphically represented here. We have to calculate the difference of these vectors, vector A minus vector B, graphically. We can take the negative of this vector B for subtracting this from vector A. Negative of vector B is opposite in direction of vector B, shown with green line. Now we can add vector A and minus vector B according to head to tail rule. So tail of vector minus B is on the head of vector A. Now we can join the tail of vector A with the head of vector B with arrowhead on the head of vector B. That gives us resultant, that is A vector minus B vector. It is actually addition of vectors that is used for subtraction of these vectors. So A plus into minus B, we added A and negative B to get A minus B vector.